So yesterday when I did the video camera comparison video, I wanted to actually include this Toshiba as well, because it would have been interesting to see what the quality of this camera was capable of delivering. Unfortunately, this one didn't work. So I guess today, this video, we can take this one apart and see what makes this thing tick. I can turn it on with the switch and the power light comes on, but I get no video signal, I get no video output from the multi-connector. So, you guys ever wanted to see what a single tube color camera looks like inside? This Toshiba IK1850C, we're going to pop this one open and take a look at what makes this thing work. Maybe we'll get lucky and I can make this thing put out a signal. Otherwise, we're just going to take it apart, see what it looks like inside. I'm also going to tear down the Sony 1800, the professional one with the bad tube. We'll take that one apart too at some future time and study the electronics on that, so you can see how much different a professional camera from a home camera was as far as how they were designed and built. But for this one, we're going to take this Toshiba apart because I've never been in one of these ones. I've had some Sony cameras apart before, but I've never been inside one of these Toshiba. So let's get the top off it and see what goes on under the covers here. The lens I've got on here, by the way, is just a closed circuit lens. It's not the right lens for this camera. I just stuck this on because the lens that was on there was kind of bulky, and I want to keep the lens closed up when it's not being used, so as to not damage the tube. It probably already is damaged, but we'll try and preserve it if we can. So I'm just going to remove all the screws in the body here. And one thing that's interesting is that Toshiba actually takes credit for the invention of the single tube color camera. Now, how a single tube color camera operates is the camera pickup tube is essentially a black and white tube, and how we generate color on the conventional broadcast cameras, you would have 3 or 4 tubes. I'm looking to see if that's got a plug on it, but of course it doesn't. Oh well, it's just the trigger grip. I think we can cut these wires. I don't think I have to worry too much about that. I want it out of the way. On the 3-tube camera, of course, you had 1 tube for each color, 1 for red, 1 for green, 1 for blue. A 4-tube camera added an extra tube for the luminance information. A single tube camera does it all with 1 tube. There's also a 2-tube camera flavor as well, which uses 1 tube for luminance and 1 tube for chroma. How they do it on a single tube camera is there's a stripe filter on the front of the tube. Red, green, blue, and they use frequency division to determine, as the electron beam is scanning the target of the CRT, because a camera tube is essentially a CRT. Works exactly the opposite way of a picture tube. Instead of having a phosphorus coating, which is illuminated by the electron beam scanning across it, in this case they have a photosensitive layer called the target, and the target has a connector on the front. It's got a metal ring on the front of the tube, and it's got a connector that connects to this photosensitive target. And as the electron beam scans the backside of the target, it changes the resistance depending on the amount of light that's landing on the actual photosensitive target. So the more light that's landing on the photosensitive target, the more current that will flow, which will cause the voltage to drop. There's a voltage applied to the target, and the beam discharges that voltage on the target. So the brighter it is, the more the discharge is, the more the voltage drops, and that is detected by the circuitry. It's really quite simple. At least it was for me when I built my first project I built in high school was a television camera. It was not a color one, it was a black and white one, but I built one from scratch, including winding the yoke coils and the focus coil by hand. Okay, so here's our circuit boards on here. This side here looks to be the chroma board. This is where the chroma signals are detected through frequency division. And on this side of the board, well, this will be our scan generator, right? Our vertical and horizontal scanning and our high voltage. And we want to see why this thing doesn't work. So I'm going to fold down these boards. So we're going to just take out these screws, which are remarkably loose. Maybe that's part of the problem. Like these are grounding screws and they're not tight at all. We're going to fold down the circuit board to reveal, well, this is part of it. This is not the tube itself. The tube is actually back here. But we'll fold down both of these boards and then we're going to try powering this thing up and see exactly what it's doing or what it's not doing, and see if we can actually make this thing work. Looks like there's been a lot of modifications done on this design after it was actually produced. If you see all these components that are mounted on the foil side of the board, like capacitors that have been added, resistors that have been added, jumper wires that have been put in. This is to create problems that arose after the unit was produced and they realized, like, oops, we messed up. This is the vidicon tube on this one. It's a type 5331. And here's some more circuitry here. Let me just take a look at this thing and we'll power it up and see whether it'll do anything at all. And if you guys are curious, this is a vidicon tube here. Okay, here's your connector where your focus, your electrostatic focus and your grid and filament and cathode are connected up to here. This tube is probably a good tube. This is for a black and white camera. I should actually put this into a camera and see how much burn-in is on it, because I think it probably was one that was used. In fact, this might have been one of the tubes from the camera that I built, because I had a couple spares. It's an S4097. I'm pretty sure this might have been the camera, one of the camera tubes are the camera that I built, because I say I did have a few spares, and I say it was the one piece of equipment that got stolen from me. I was using the camera as it was designed. It was a security camera, and I actually had the camera mounted in front of my parents' house, because I was in high school at the time, and this was my little pride and joy. I built this little camera and I had it hanging out in front of their house, or had it mounted up in front of their house, pointed at their front door so that we could see. We could go onto the TV and we could see if there was anybody at the front door from the back. And some holes, pardon my French, one Friday night decided that they wanted the camera more than me, and they snuck onto the property and they climbed up on some milk crates, and they took the camera and just cut the wires and left it and took the thing. And it was something that I had built and I had spent months. And when I say built, I mean I built everything. I wound the coil by hand. It was wound on a piece of a toilet roll, tissue roll. The coil was wound on that. Everything was wound by hand. Everything was done by hand. Here's the tube in this one here. As you can see, it's the same size of tube as I've got here. But anyway, here's your different components. Okay, here's this is your electrostatic focus down here. So that's what these leads here that are connected. These are connected to the focus grids. So this is what focuses the beam as it's traveling down the tube. And this area up front here, this is called the target. And here's the metal ring. So here's your photosensitive surface that's behind here. And that is electrically connected to this metal ring here. This is the target. So there's actually a connector. When it sits inside the socket, there's actually a connector on the front here, which is applying a high voltage through a very high ohms resistor. I think it was like 1.5 mega ohms or something. It was quite high, but that gives it a very high impedance. And then there's a field effect transistor that was, the gate was also connected, coupled to this target. So as the beam discharged the target, it would discharge more where there was light hitting it and discharge less where there was less light hitting it, and that would cause a waveform that would be inversely proportional to the amount of light. So it would cause a voltage drop If there was no light at all, if it was covered up, you'd have full voltage, full DC. But if you had full white, it would drop it right down. So you'd get a video signal. My camera's having trouble focusing here. That's why I usually turn the autofocus off on this thing. Your video signal would vary depending on the light on the target as the beam scanned top to bottom, or left to right, top to bottom. Anyway, there's a camera tube. Let's take a look at this other thing here. Incidentally, that camera tube is the same tube that Hitachi camera. I believe it uses the same tube as that. And I think my Ikigami, also I have an Ikigami one. That Ikigami camera that I showed previous, that I fixed it once before, and I've kind of misplaced it now, but that Ikigami black and white camera that I fixed on a video a while back, that was actually the camera that I replaced the one that was stolen with. This camera uses the same power as a Sony, so I've got the Sony power supply here. We'll plug that in and turn it on and see if I get any type of signal. I'm just going to hook the scope up because I'm not getting any video, but I want to see whether I'm getting anything out the video terminal on the scope. And just as I thought, there's just noise there. Nothing. No sync, no video signal, no nothing. There's just noise. So, first things first, let's see if there's any internal fuses blown on this thing. So of course, whenever I see things that say high voltage, dangerous, I get excited because I like high voltage. Here's our flyback transformer here. Let's see if we got anything on here. I'm going to use my scope again on the times 10 reference so I don't blow anything up. If I do have voltage on here, we'll just hook up our ground for the scope. This should be the collector from the... Yeah, I'm not getting any oscillation. If we watch, I'll show you what the scope is doing here when I turn on the power on and off. Okay, if you look at the scope, when I flip the power on, watch what happens. I'm just getting a rise, and then it comes back down. The reason for that is my scope's in AC mode. If I put my scope in DC mode, and we'll just zero it out here. You see, I'm getting my B+, but that's all. And then when I turn it off, my B+ is dropping. I have no oscillation, and this should be, I believe this should be the horizontal oscillator here. Check out some of these custom modules. This was quite common back in the early 80s, where a company would make these little glass boards, composite modules. You know, they were a custom IC, but not a large scale integration. And this camera's got a few of them in here. Here's another one back here, right? This is a resistor array. You can see, if you look at it, you can actually see. Let me see if I can get the camera to focus on here a bit better. But you can see this is a resistor array, and you can actually see the traces. Find something to point with here. You see these traces here. This is a resistor array, and the longer this is, that changes the resistance. This was again quite common on a lot of these old electronics, especially a lot of the old cameras, was they use these custom in-house made modules because nobody else was making them. If you were building this electronic stuff, you had to actually design your own circuitry. You couldn't just go out to a parts manufacturer and say, give me this particular part. And until there was a demand for those parts, they were made in low volume and they were made in-house, such as this one right here. This blue, and you can see it's got a 8-pin dip. What's it got on it, I wonder? I'm just going to take a look and see what this is. Now, of course, an LM359, that's a general purpose amplifier. I think this is probably the vertical. That's what that's going to be. A vertical size right here. This is the module here. This is vertical size. This is going to be the vertical output module. So they just use a little audio amplifier down here for the vertical output. You know, unlike a CRT, which needs a lot of current, camera tube doesn't need much as far as deflection goes, right? So basic off-the-shelf little audio amplifier and a couple support components, and there's your vertical output. I just found something kind of interesting here. The date that the plastic was molded was January 23rd, 1980. So this camera would have been manufactured around 1980, I would guess, or in that year. Because typically they would make parts to arrive around the time the thing was being manufactured. Toshiba would have put in the order with this company to make this plastic part for cameras in production. So you gotta figure this camera was probably, you know, January, February 1980 was when this camera was manufactured. So that would make this camera 36 years old. Here's something else you don't see very often. This IC is socketed. This Toshiba T2539 IC, this is probably in the color processing circuit. This is a socketed IC, and typically companies don't go to the trouble and expense of putting in a socket on an IC unless they expect that that might be a part that's going to be a problem, and that might be a part that needs to be serviced from time to time. So if it's a part they expect is going to be a high failure part, they would mount it in a socket so that if it went into the shop, the technician could just swap it out and pop a new one in. So that's clues right there that they were thinking about service at the time when this was made. And this was a part that I guess they figured would be one that would be problematic. So they put it in a socket. Well, I'm getting somewhere. I've got voltage is missing here, and I'm tracing it back to this back board back here. When I measure my standby switch, one side goes to 12 volts when I turn it on, and back to 0 when I turn it off. But the other side, I'm not getting any voltage on there, and I'm thinking that is supposed to, when I turn it off, it goes to like 1.3 volts. You can see the meter there. Right, when I turn this on, this goes down to 0, and I have a feeling that that might be a supply, because when I bridge it to 12 volts, I get video. I'm not getting a picture, but I'm getting a screen lighting up on the TV. If I show you here, if I just short the two tops of this switch together, and this is the one here. I think this is probably supposed to be my supply. The center conductor here, the center pin of the switch. I think this is supposed to be my supply. It's hard when you don't have schematics. It's got 1.7 volts. When I turn the switch up, it goes to nothing. The other side of the switch here has got 12 volts on it. If I bridge the two of those together and turn it on, I'll show you what happens on the screen. Okay, when I bridge those two together, I get that. Like the camera's turning on and I got sync. The tube's not unfolding, but I got sync. Well, what I've traced is this connector here that plugs in here. This goes to that side of the switch. I'm just going to pull this board out here. This has got to be part of the power supply. These screws are all loose too. That might be something to do with it, but let's just lift this board out and take a look at the other side of this board, if I can get it out of here. And just see where this brown wire is connected. Check this out. I picked up this light probably, I don't know, 15, 20 years ago off eBay for $10. It's a 70 watt ceramic metal halide light. I finally got around. I was using it in my other workshop, had it on a stand. I used it as a studio light for years, and because it gives off a nice warm light. But look at that! I'm constantly fighting to see what I'm doing on this bench, because I've got my fluorescent lights are overhead and they light up the bench nicely, but they don't give me a lot of light for what I'm looking at. So I'm always using this thing to try and see what's going on, right? Trying to get extra light and to see things. I figured I'm going to grab this light. I had it mounted on a stand, and I just took it off the stand and stuck a screw into the ceiling and fired it up. And it's like, well, this makes quite a difference. I can actually see things a lot better now. I'm still troubleshooting this thing. I'm missing a voltage, and I know that if I bridge my 12 volts to one of the connectors over here, I get it. The camera comes on. I don't get a picture, but I get everything else on. So I'm back onto this power supply board here, basically tracing wires to see where they go. It'd be really nice if I had a schematic. I don't. So when you don't have a schematic, you have to follow traces, and it can take a while. It's really quite time consuming to figure this out. So here we have our horizontal drive pulses. Where are we here? Okay, those are our horizontal drive pulses coming off the driver transistor, which is right over here. I should charge the base to the driver transistor, and it goes to the emitter here. The emitter pulses are also there. So we have our emitter pulses, and they should come back over to here on the board, which they do, which you'll see if I point up the scope here, you'll see we have our drive pulse, and that should be driving the base, but it's not. It's not driving the base of my output transistor, which is this one right here. The transistor tests okay. So I'm going to take a look at this because I've got my drive pulse right here. And it goes through a couple components here. It should drive that transistor, which should drive the flyback transformer to produce the high voltages for the tube, which I'm not getting. So I got to look and see what components are in here. It doesn't look like there's much. It's like maybe a capacitor. Resistor and a diode and the transistor, it looks like. What is this little cap? Where is that? Looks like there might be a little cap there, actually. Maybe that's the problem. There's a small little electrolytic cap right there. You can see it. This little bloody thing right down there. Little 10 volt, what is it? 10 volt, 220 or 222? 22 microfarad at 10 volt. Check the ESR meter. Just take a look at that thing. Wouldn't that be weird if that was causing me to lose my drive? That little cap. Wouldn't that be weird if that was the whole problem, keeping this camera from turning on? After some more tests on here, I found the problem with this one is this transformer is shot. If we look at the resistance of the coil here, where am I here? 0.9 ohms. And 10 ohms on that one. The primary is shorted, and watch what happens when I force it to power up. If I leave it run for more than a few seconds, the thing will start to probably smoke. So we'll just power it up here. Just keep an eye down in here. You'll see some smoke start to come up out of this area of the transformer. What's happening is it's drawing too much current. That's why I have no high voltage. There, you see? Transformer is now getting hot. You can see the smoke coming up here. So this one is not going to be repairable, which is good because this makes a great teardown project. So let's take it apart. Let's see what all the boards and everything do on this one. So I guess the first thing we'll do is we'll remove the preamp. This is the preamp that would amplify the signal off the vidicon tube. Get the screws out of it. Pop the top off and look at the preamp. This should just be a shield. There we go. So here's the preamp. Here's where the target connects. So this little wire is the one that goes to the ring on the tube. This is the low noise preamp. Amplifies the signal. And then sends it off to the chroma board on the other side over here. So unplug a couple of these connectors here, and if I want to remove the tube, I just have to remove the lens, and I should be able to remove the color filter. I think that's the filter on the front here, or the lens mount. What's kind of neat about this particular camera is this one actually used our standard C-mount lens, which is something that not too many home video cameras did, but this one did. Okay, now on here, this piece here. This is actually the infrared cut filter. This is not the. This piece is not the color stripe filter. This is the infrared cut filter. So what this does is this removes. You can see the dichroic coating on there. This just removes infrared. But inside here, you'll actually see on the front of the tube, you should be able to see the mask, the color stripe filter. If we get the angle of the light just right, you should be able to see you can see the mask on the front of it. We take out this gasket here. So now you can see the whole front of the tube with the integrated color mask on the tube. Now if I unplug the tube, which I can do by just doing the tube socket back here, and if I undo the clamp, you should be able to actually push the tube right out. So if I undo the clamp, I think that's the one that holds it in place. I should be able to just, oh, there's another one up here. There's another screw up front here I gotta take out. Here's the tube clamp is right there. I loosen off the tube clamp. I can push the vidicon tube out of the camera. And there is the Toshiba color vidicon, single tube color vidicon. It's a E5331, which is what it says right here on the yoke coil. Now, of course, alignment of these things is absolutely critical when they're put in, because obviously if you're not square, I'm trying to find my sweet spot here to show this off, but if you're not square, if your tube is tilted in any which way, you know, from being exactly center, your scanning beam is going to scan. You're going to be off, so that's going to affect your color. So the setup on these was quite critical, that your tube was actually put in the correct orientation. For a black and white tube, it doesn't matter, but as you can see on the front of this thing here, you can actually see there's a good shot of it right there. That's a good shot of the color filter. So basically, if we were to look at this under a microscope, you would see individual red, green, and blue stripes. Now, indeed, when I look at it with a magnifying glass, I can actually see, I don't know if we're going to be able to get it off camera here, probably not enough light, but I can actually see the individual pixels with this magnifying glass. I don't think we're going to be able to see it on camera here, but in fact I guarantee you we won't be able to see it on the camera. But if I put this up to my eye and I look at this tube, I can see the actual dots. I can't see the individual pixels, but I can see the dots on the tube, on the surface of the tube. But anyway, that's your color vidicon, and I bet you this color vidicon could be put into a black and white camera and it would perform and just give you black and white. But each of the pixels would be registered to one of the colors. That's upside down. Normally this was in. It came out of the camera like this. You can see the reflection at the bottom here. You can see the actual color filters, right? Blue, green, cyan, yellow, and one with no. Looks like, or blue, red. Sorry, it's probably magenta. It's hard to tell in the reflection here, but looks like blue, red, cyan, yellow, and then one without. And that's how they reference it. Anyway, that's the vidicon out of this. I actually can hang on to that part. And of course there's the infrared cut filter that it would sit behind. I'm going to hang on to the tube. The rest of the camera can go into the recycle bin because there's not really much use in this. One thing that is interesting is the size difference between a monochrome tube and a color tube. And these tubes were not cheap. Like the majority of the cost of the camera was the actual tube itself. Even in black and white cameras, these tubes were a couple $100, but the color tubes like this, like a tube like this would probably be, if you burned your tube and had to have the tube replaced, which was easy to do if you pointed your camera at the sun, for example, it would easily cost you probably $400 to $500 just for the tube. They were ridiculously expensive. Now mind you, I'm just referring to the single vidicon type tubes. If you had a broadcast camera that used, say, Plemicon tubes, you were talking several $1,000s to change the tubes on them. Exceptionally expensive. So of course, you know what we do with things that you know what we do with things that we don't fix here, right? Bye. That one's off to the dump. I kept the only part of it that was actually that might be useful for something. Let's get on to the next project. What do you say? So you remember this one? This has got it's even got more lines on it now from when I shot the video. This is the one that's got it's got some lines on this picture. Let's take this one apart. This one works, so it gives us something that we can kind of play around with and see what we can do on this one. See if I can get it to look any better than that. I mean, it looks pretty sad now, but again, this is another camera that doesn't owe me anything. It doesn't have really any value other than the fact that we can tinker around with it. But let's take this one apart. I just realized something. I've got so much light in here with this work light that I just put in. This 70 watt ceramic metal halide that I can operate with the garage lights out, and it's like being in a studio. Everything around me is dark because it's dark out now, right? It's nighttime. I can work in here with just this with this one light on and have more than enough light for everything. So we saw the way that Toshiba built a camera. Let's look at the way that Sony builds their camera. And lift the grip off, unplug it, and then the side of the camera comes off. You can unplug those connectors, remove the knobs, and this side comes off. So we saw Toshiba's design. Here's how Sony does things a little differently. One of the drawbacks to working outside at night with the door open, because it's pretty warm out here, is that I have to deal with mosquitoes. So I have this little beauty here. Does this thing work? Well, you tell me. It definitely, it works. I got bugs flying around here right now. Come on, little bugger, come and get it. Come and get it. Come to dinner. Oh, you're on my... There we go. Gotcha. On the Sony, we'll undo the screws to hold the board in and fold down one of the boards. As you can see, again, designed for service. These connectors you see, these are the ones that went to the grip on the side of the camera. Here's our tube. I have a feeling that the bias is maybe off on this tube because it looks like it's under biased. So maybe we can adjust that There'll be some controls on here. I'm just looking to see which ones are which. They're not clearly marked, but there will be a beam control in here. There'll be a target control. Let's take the other side off here to take a look at what's on this side. As you can see, Sony have a lot more ICs in this camera than the Toshiba. The Toshiba had a lot more regular just transistors. The Sony is a little more highly integrated. On this camera, this looks to be the video board, video and color process board. This board over here is going to have all the high voltage generation, and the sweep is going to be on this board. So my beam control, I'm thinking it's going to be on this other board here. So I pulled this one out to take a look at it, but I don't think I need to. I don't think I need to keep this board out. I can probably put that one back in place, and I didn't need to take these off of the controls either. I only had to undo this bracket, but I took them off anyway. But maybe I'll put them back on. This is the color balance adjustments, and the iris adjustment is what this is. I'm just putting a few extra screws in, and I took out a few that I didn't need to take out, so I'm just going to put them back in, and then I'm going to power this thing up apart and see whether we can find the appropriate control to adjust the beam, because again, they're not labeled. So let's power the camera up and see whether I get a picture. Well, I'll get a picture, but see if I can find the adjustment. So on here, if I start to tweak, you'll see that if I adjust this one, this is actually the vertical size. It'll change the picture. It'll change the size of the picture. Now it's a vertical linearity. That was the vertical centering. That was the horizontal size. Horizontal linearity. Haven't found the beam control just yet, but we'll find it. It's got to be one of these ones in here somewhere. See, it would have been nice if Sony had labeled their controls. Here's something interesting. One of my controls here is kind of loose when I touch it. It shifts the color. Going back onto the other side here, to this board over here, and we'll try looking for the control for the beam. You'll know when I hit the beam one because the picture will wash right out when that was obviously a peaking control. The picture will wash right out when I hit the right one. As I just go white. Remember I said this unit had the reversal switch, so if I throw the reversal switch, now everything becomes negative. So that was one of the strengths of this little camera. And Sony actually had a little adapter that they sold called a Photolab adapter. And what it allowed you to do was take color negative film, and it had little trays that you would lay the color negative film in, and it used like a regular incandescent light bulb with a couple filters to filter out the infrared. And it would shine through the negative, and it had a lens assembly that went right into the lens on the camera. And you could flip it to negative and turn color negatives into video, into positives. And you could also do slides. You could push slides through it as well. I think this thing looks a little bit better now. The green lines that were at the bottom when I did the demo yesterday, I know it doesn't look great on the plasma because I'm shooting it with the camera, but the green lines that were at the bottom, I've gotten rid of them. And this actually doesn't look too shabby now. But here's the beam control. When you turn the beam, it'll actually bloom the picture. So if the beam is too low, it'll actually rotate the picture while it's doing it too, but if the beam is too low, and you get into that sweet spot where the color just pops, see that? There we go. That's when we're at optimum beam current, because it affects the focus as well if the beam is too low. It's actually RV10. Again, it's not labeled on the stupid thing, but it's this one right here. That's the one there that adjusts the beam, and there should be another one for target on this thing. This one's back focus, so when you adjust that one, it actually moves the pickup tube back and forth. So when you're on a wide shot, it'll affect your focus. Or is that tilt? That might be tilt on the tube. Back focus is over here. Here's the back focus adjustment here. You loosen off these screws and you can move the lens back and forth. This control here, this is tilt. So that's for when you've changed the tube and you need to align the tube for the color stripes, you can rotate the tube physically to get your picture to line up. Working on cameras, you basically needed to have a light box to do the alignment on cameras, because if you didn't have a light box, you're never going to get your alignment correct. And a light box basically was a box that had a light in it, and it had a series of stained glass panels that looked just like your color bars on your NTSC color bar generator. It had the colors arranged in the same order, and they were pieces of stained glass, and you focused your camera on it. And that was what was used for adjusting your chroma level and phase and subcarrier phase and all that stuff. You shot a color chart that was illuminated from the back in a light box. So to work on cameras, you needed that. I'm just looking to see if I can find any test points on here so we can scope this thing and take a look at some of the signals. So now if we look at the delay line 2 here, what we'll see here is we'll see video before sync is added. Cat's going to get electrocuted. So there's video before sync. Here we're looking at some timing pulses. These pulses are used for separating the colors. And basically what they do is, as the beam is scanning the surface of the tube, because the surface of the tube's got the stripes, the color stripes, so as the beam is traveling across the surface of the tube, the timing pulses are switching a matrix to switch between the red, green, and blue channels to generate the color signal. And those are signals there that are coming off of that clock timing generator that are used to switch between one channel and the next. And that's these ones over here. Here we are looking at raw video going into the matrix IC, so we can look at the different levels here. This is the video signal, how it gets processed. This is the chip there. There's some chroma signals there. Or one will be the Y minus blue, one will be a Y minus red. Sync. That's probably the luminance channel. And see, the sync hasn't been added to the video at this point. Video is being processed before it is being multiplexed into a full composite signal. There's chroma. Horizontal sync. And then the sync gets added later on another chip. Chroma. Chroma. this sync. That could be the clock. That's a clock signal. That's for the color separation. That looks like composite sync there. Yeah, there's a composite sync. There's your horizontal pulses along with the vertical pulses. So those are the vertical pulses. That's composite sync. I should have composite video somewhere in here too. This is the sync pulse and clock generator that I'm looking at, IC8. I was looking for where the signal actually gets multiplexed together, where our composite sync and video are added. I think that's it there. Yeah, there's our composite sync and video on IC5. So our sync and video is mixed together on IC5. Our sync is generated over here on IC8. Our chroma is processed down here, and this is where our raw video goes in. Looks like this was raw video here, right off the vidicon, and it's processed in this and comes up onto this chip here. Yeah, and if I flip the inversion switch, you can see this one's doing the inversion. And that's where everything is mixed together. Anyway, that's the basics of this Sony 2400. And of course you saw the other one ripped all apart. Hope you enjoyed this look at the old tube camera. I know a few of you made requests to take a look at the tube camera, so there you go. Now you've seen one. I'm probably going to tear down the 1800 as well. I'll do that on another video because that's the professional camera. We'll swing some of the boards out on that one and take a good look at that one. But these were a couple of home cameras here. I figured I would just tear them down and show you guys what goes on inside them. I hope you enjoyed this video. We'll catch you in the next one. Bye.